Welcome to Dreaming Scientist's Sleepy Stories, a place where the mysteries of the universe guide you toward peaceful sleep. At this very moment, our galaxy is not drifting quietly in place. The Milky Way is traveling through space at a speed close to 600 kilometers per second, moving toward a region we cannot directly see. This motion is not guessed, and it is not theoretical. It is measured repeatedly, confirmed across decades, and revealed through entirely different kinds of observations that all point in the same direction. One of the clearest signs comes from the oldest light in the universe. The cosmic microwave background surrounds us like a faint afterglow, released when the universe was still young and cooling. It should appear almost identical in every direction. Yet careful measurements show a slight imbalance. One side of the sky appears subtly warmer, the opposite side slightly cooler. This pattern is not noise. It is the signature of motion. When early satellites first detected this imbalance, the simplest explanation emerged naturally. Our galaxy, along with its neighbors, is moving relative to that ancient light. Later missions refined the measurement. Improved instruments narrowed the uncertainty. Space observatories confirmed both the direction and the speed with remarkable consistency. Together, these observations reveal that the Milky Way and the entire local group are drifting toward a region of sky near the constellations Centaurus and Norma. That conclusion has not changed with time. It has only grown more precise. At first, astronomers searched nearby for the cause. The gravitational interaction with our closest large neighbor contributes slightly. The influence of nearby galaxy clusters adds more. But when these effects are added together, they fall short. The numbers refuse to balance. Something larger, more distant, and more massive must be shaping the motion. This realization shifted the problem from individual galaxies to the structure of space itself. Instead of asking what pulls on the Milky Way, astronomers began asking how entire regions of the universe move together. To answer that, they turned to large surveys that measured not only where galaxies are, but how fast they travel. As redshift catalogs expanded, a pattern slowly emerged. Galaxies did not move randomly. Groups of them shared similar deviations from cosmic expansion. When these motions were mapped in 3 dimensions, they formed gentle streams rather than scattered vectors. Many of these streams pointed toward the same obscured region of the sky, hidden behind the thick dust and stars of our own galactic plane. This obscured zone became a challenge. Optical telescopes could not see through it. So astronomers changed their approach. Radio observations revealed galaxies concealed by dust. X-ray instruments detected vast clouds of hot gas trapped in deep gravitational wells. Infrared surveys filled in additional details. Together, these observations uncovered a massive concentration of matter near a rich galaxy cluster in the Norma region. What emerged was not a single object, but a broad gravitational basin. Thousands of galaxies, enormous reservoirs of hot gas, and far more dark matter than visible material combined to create a powerful influence. This region became known as the Great Attractor, not because it is mysterious, but because its gravitational effect is unmistakable. According to general relativity, mass reshapes spacetime. When mass is distributed unevenly, it guides motion across immense distances. The Great Attractor does exactly this. Its influence extends across tens of millions of parsecs, gently redirecting the paths of entire galaxy groups, including our own. Further confirmation arrived when astronomers reconstructed velocity fields using independent methods. By comparing measured distances with expected expansion speeds, they built maps of how galaxies actually move. These reconstructions revealed long, coherent flows threading the local universe. Many of these paths curve toward the same dense region before continuing onward, like water following the contours of a hidden landscape. The Milky Way fits seamlessly into this pattern. It is not behaving unusually. It is responding to gravity exactly as physics predicts. Dark matter plays a central role in this behavior. Although invisible, its presence is inferred through motion, temperature, and structure. In the Great Attractor region, dark matter outweighs luminous matter several times over, providing the dominant contribution to the gravitational field. Independent teams, using different datasets and techniques, recover similar results. The direction remains consistent. The speed remains similar. While uncertainties exist in detail, the overall picture is stable. Our galaxy is moving because spacetime itself is shaped by a vast, uneven distribution of mass. As new surveys deepen and instruments improve, the view continues to sharpen. Modern observatories are revealing structure in regions once hidden. Each new observation reinforces the same conclusion. The Milky Way's motion is not accidental. It is part of a larger cosmic flow. As astronomers traced this motion backward through observation and inference, a quiet realization emerged. This strange behavior had been hiding in the data for decades, unnoticed at first. And that realization leads naturally into the next chapter of the story. How did astronomers first recognize that galaxies were not moving as expected? The earliest clue did not arrive as a dramatic discovery. It appeared instead as a subtle mismatch in carefully recorded measurements. By the mid-20th century, astronomers believed they understood the large-scale motion of galaxies. Space was expanding, and distant galaxies should recede smoothly according to their distance. For a time, the data agreed. But as distance measurements improved, small deviations appeared. Galaxies were drifting faster or slower than expansion alone could explain. These extra motions were not random. They followed patterns. By separating expansion from additional movement, astronomers uncovered what became known as peculiar velocities. These quiet discrepancies marked the first indication that something vast and unseen was shaping the motion of the universe around us. And with that realization, the deeper investigation truly began. The motions were not called peculiar because they were uncommon. They earned that name because they refused to fit the tidy expectations astronomers once held. Small irregularities were always anticipated. Nearby galaxies tug on one another. Clusters create local distortions. Minor deviations from cosmic expansion were never a problem. What unsettled researchers was something far larger and far more organized. By the late 1970s, astronomers were no longer studying galaxies in isolation. Teams led by researchers such as Alan Dressler and Donald Lindenbell began assembling extensive catalogs that tracked galaxy motions across vast portions of the sky. When these measurements were plotted together, an unexpected coherence appeared. Galaxies separated by tens of millions of light-years showed similar departures from pure expansion. They were not merely drifting away from us. They were sliding together, sharing a common direction of motion. At first, caution dominated the response. Astronomy has learned, through hard experience, that patterns can emerge from incomplete data. Distance measurements were still imprecise. Selection biases lurked in every survey. A false signal was always possible. But as additional teams repeated the measurements using different methods, the same directional trends returned again and again. A major turning point came with the rise of infrared astronomy. When the IRIS satellite surveyed the sky in the early 1980s, it revealed thousands of galaxies hidden behind dust that blocks visible light. When these newly discovered systems were incorporated into redshift catalogs, the large-scale flow did not disappear. It sharpened. The motions pointed toward a region long obscured by the dense foreground of our own galaxy. That region lay behind the crowded plain of the Milky Way, where stars, gas, and dust overwhelm optical observations. Astronomers had long referred to this area as the zone of avoidance, not out of mystery, but necessity. Traditional surveys simply could not see through it. Gravity, however, does not respect observational blind spots. If mass was concentrated there, its influence would extend outward regardless of whether telescopes could detect it directly. As redshift surveys expanded through the 1980s, the evidence accumulated. Thousands of galaxies, then tens of thousands, were mapped. Each new dataset reinforced the same conclusion. The deviations were not random noise. They formed a coherent flow. Galaxies were moving as though responding to a large gravitational pull emerging from a partially hidden direction. One of the strongest confirmations came from an entirely different reference frame. The cosmic microwave background provides a universal standard for motion. When astronomers compared galaxy velocities to this ancient radiation, they found the same offset. The Milky Way, the local group, and many neighboring groups shared a common drift relative to the background. Two independent lines of evidence, galaxy surveys and primordial radiation, converged on the same story. As computational tools improved, astronomers shifted their approach. Rather than analyzing galaxies one at a time, they reconstructed velocity fields, treating motion as a continuous flow across space. These reconstructions revealed long, stream-like paths bending toward the same obscured region. The idea of a gravitational attractor did not arise from speculation. It emerged naturally from the structure of the data. The term Great Attractor was never meant as a final answer. It was a placeholder, a descriptive label for the source of the observed pull while its nature remained uncertain. What mattered was the implication. Galaxy motions were tracing mass on scales far larger than individual clusters. Healthy skepticism persisted. Astronomers tested whether known structures, such as the Virgo cluster or the Hydra-Centaurus region, could explain the flow. Detailed modeling showed that while these regions contributed, they were insufficient. The magnitude and direction of the motion required something more massive or more extended. The decisive shift came when observations across multiple wavelengths aligned. X-ray telescopes detected vast reservoirs of hot gas trapped in deep gravitational wells behind the Milky Way. Radio surveys revealed clusters aligned with the inferred flow. Each method reduced the chance that the pattern was an artifact. The picture became harder to dismiss. A new understanding followed. Galaxies do not simply ride the expansion of the universe like passengers on a moving platform. They respond continuously to uneven mass distribution. Where matter concentrates, space-time curves more strongly, and motion adjusts accordingly. The peculiar velocities were not errors. They were signals. This realization transformed how astronomers treated redshift data. Instead of averaging deviations away, they began using them as tools. Differences between expected expansion and actual motion became a way to map unseen mass, even where light failed to reveal it. The path to this conclusion was slow and deliberate. For decades, astronomers resisted drawing bold claims from incomplete maps. Distance indicators were refined. Surveys were cross-checked. Independent confirmations were demanded. The recognition of large-scale flow was not the result of a single discovery, but of many careful steps taken over many years. By the end of the 20th century, the pattern was unmistakable. Galaxy motions across hundreds of millions of light-years showed coordination. Cosmic expansion was real, but it was not the entire story. Beneath it lay a gravitational landscape shaped by invisible structure. Later analyses summarized this insight succinctly. Galaxy velocities offer one of the most direct ways to trace mass in the universe, including matter that emits no light. Space missions and ground-based surveys steadily improved resolution and confidence, reinforcing the same conclusion. What began as a nuisance in the data became a guide. Peculiar velocities, once treated as complications, became signposts pointing toward the deepest mass concentrations nearby. The realization that galaxies were moving the wrong way was, in truth, the realization that astronomers had been looking at the universe from too narrow a frame. As velocity maps grew more complete, another tension emerged. The region drawing galaxies inward did not appear to be the final destination of the flow. Beyond it, the data hinted at even larger structures exerting influence from farther away. That unresolved tension opens the next chapter. Why is one of the strongest gravitational influences in our cosmic neighborhood hidden behind the glare of our own galaxy? The frustration surrounding the Great Attractor is not about its distance or even its mass. It is about its location. From Earth, our view toward this region passes directly through the brightest and densest part of the Milky Way, where dust absorbs light and stars crowd every line of sight. For much of modern astronomy, this made the attractor effectively invisible. On optical maps, the region appeared empty. Yet gravity told a different story. The apparent void was not a lack of structure, but a limitation of observation. And it is precisely this mismatch, between what we see and what we feel gravitationally, that deepens the mystery and leads us onward. The path toward clarity did not begin with sharper eyes, but with broader vision. To understand what lay hidden, astronomy had to move beyond visible light. Dust that blinds optical telescopes is largely transparent to longer wavelengths, and this simple fact opened a quiet doorway forward. Radio astronomy provided the first glimpse through the obstruction. In the closing decades of the 20th century, instruments such as the Parkes radio telescope began surveying the sky for the faint signature of neutral hydrogen. This emission, stretching across long wavelengths, slips easily through the Milky Way's dust. What emerged from these surveys was unexpected. Galaxies were present where optical maps had shown emptiness. The so-called zone of avoidance was not empty at all. It was simply unseen. As radio maps expanded, continuity appeared. Galaxy distributions flowed smoothly across the obscured region, connecting structures on either side of the Milky Way's disk. Clusters aligned naturally with the direction indicated by large-scale galaxy motions. The gravitational pull inferred from velocity measurements now had visible counterparts. This was an early but decisive signal that the Great Attractor was not a mathematical abstraction. It was a real accumulation of matter, hidden only by foreground dust. X-ray astronomy added a deeper layer of confirmation. Galaxy clusters are not merely collections of stars. They are vast reservoirs of superheated gas, reaching temperatures of tens of millions of degrees. At these extremes, gas shines in X-rays, a form of light capable of passing through dust that blocks visible wavelengths. Satellites such as Rosat, followed by NASA's Chandra X-ray Observatory, detected bright X-ray sources precisely where gravitational models predicted deep wells of mass. Among these detections, one structure stood out. The Norma cluster, also catalogued as Able 3627, emerged as a dominant presence. Located roughly 65 million light-years away, it ranks among the most massive clusters in the local universe. X-ray observations revealed gas confined tightly by gravity, signaling a massive halo of dark matter far outweighing the visible galaxies within it. Norma appeared not as an isolated peak, but as an anchor within a wider region of excess mass. Infrared astronomy refined the picture further. Infrared light occupies a middle ground, slipping through dust more effectively than visible light while still tracing stars directly. Missions such as NASA's Spitzer Space Telescope and ESA's infrared observatories uncovered thousands of galaxies whose light had been reddened and dimmed, yet not erased. Each detection filled another gap in the obscured landscape. Taken together, these observations transformed understanding. The zone of avoidance was no longer a void. It became a partially revealed terrain, assembled piece by piece through different windows of the electromagnetic spectrum. No single wavelength could capture the whole structure. Radio surveys traced gas-rich systems. X-ray telescopes highlighted the deepest gravitational wells. Infrared instruments revealed stellar populations buried behind dust. Only by layering these views could astronomers approach a coherent picture. This process demanded restraint. Each dataset carried its own limitations. Radio surveys favored certain galaxy types. X-ray observations emphasized massive clusters while overlooking diffuse filaments. Infrared maps revealed stars but said little about dark matter directly. Interpretation required care, cross-checking, and patience. As computing power advanced, synthesis became possible. Scientists began integrating these datasets into three-dimensional reconstructions. Galaxy positions were combined with velocity measurements, allowing mass distributions to be inferred indirectly. Time and again, these models revealed a dense region aligned with the direction traced by peculiar velocity flows. NASA has described this approach simply and elegantly. Galaxies act as test particles. Their motions trace invisible contours of gravity, revealing structures even where light remains incomplete. This principle now underpins much of modern cosmology. Motion becomes a map where brightness fails. The challenge of looking through the Milky Way reshaped future missions as well. The Gaia spacecraft, though designed to chart stars within our galaxy, contributed indirectly by refining models of the Milky Way's structure and dust distribution. With a clearer understanding of the foreground, astronomers could better correct for its obscuring effects when studying the universe beyond. More recently, high-resolution radio facilities such as the Atacama Large Millimeter Array have continued the work. These instruments reveal finer details within the hidden region, exposing smaller structures embedded within the larger mass concentration. Each improvement narrows uncertainty and sharpens the outline of what lies behind the galactic glare. Even now, the Great Attractor resists clean definition. It has no sharp edge. It is not a single object that can be circled on a map. It is a region where matter accumulates above the cosmic average, part of the vast web of filaments and nodes that shape the universe on the largest scales. This difficulty brought an unexpected benefit. Forced to look beyond brightness, astronomers learned to trust dynamics. By following how galaxies move rather than how they shine, science uncovered structures otherwise invisible. This shift reshaped studies of dark matter, cosmic flows, and the architecture of the universe itself. There is also a lesson in perspective. From Earth, the Milky Way dominates the sky, a luminous band that defines our night. Yet that same beauty hides forces shaping our motion through space. The structure that marks our home also conceals nearby giants. As Carl Sagan once reflected in another context, our view is shaped by where we stand and how briefly we observe. The Great Attractor reminds us that limits of vision are not limits of reality. Today, the region is no longer fully hidden. Its outline grows clearer with each survey, though gaps remain. Future missions will continue refining its mass and extent. The Milky Way's glare still complicates the view, but it no longer blinds us completely. As astronomers assembled these fragments, a broader realization emerged. The Great Attractor is not an isolated anomaly. It is part of a larger gravitational landscape, one whose influence stretches beyond the hidden region toward even greater concentrations farther away. That realization leads naturally to the next question. Is the Great Attractor a single cosmic giant, or an entire continent of galaxies? For many years, it was imagined as one enormous object, a hidden monster drawing everything toward a single point. The image was compelling, but the data slowly dissolved it. As observations improved, no single structure proved massive or compact enough to explain the motions alone. Instead, the region resolved into many dense components working together. The pull arose not from one core, but from an extended network. The Norma cluster remains a central player, but it is embedded within a broader system. Around it lies a complex arrangement of clusters and galaxy groups forming part of the Hydra, Centaurus region. This structure stretches across tens of millions of light years, woven together by filaments of matter. What astronomers uncovered was not a solitary object, but a landscape. A region where mass gathers, gravity deepens, and galaxies slowly adjust their paths, quietly, continuously, and without spectacle, as the universe patiently shapes its own motion. You begin this journey not by looking harder, but by learning to look differently. For a long time, the sky seemed incomplete. A wide band of darkness cut across our maps of the universe, where the Milky Way's dense dust and stars blocked the view beyond. Astronomers called it the zone of avoidance, as if the cosmos itself had chosen silence there. Yet gravity did not respect that silence. Galaxies nearby drifted, subtly but persistently, pulled toward something hidden. To understand that pull, science had to learn how to see without relying on light alone. You drift first into the realm of radio waves. These long, patient wavelengths slip easily through dust, carrying whispers of neutral hydrogen from distant galaxies. In the late 20th century, radio telescopes began to listen. Slowly, shapes appeared where emptiness was once assumed. Galaxies emerged behind the Milky Way's glare, arranged not randomly, but along continuous structures that crossed the hidden region. The supposed gap was never real. It was only unseen. As radio maps deepened, they revealed alignments, clusters arranged along the same direction as the mysterious gravitational tug. The idea of the Great Attractor shifted from speculation to substance. Something massive was there, concealed but undeniable. Then your attention turns upward, into the high-energy glow of X-rays. Massive clusters of galaxies hold vast oceans of gas, heated to extreme temperatures as gravity squeezes it tight. This gas shines brightly in X-rays, which pass through dust almost without resistance. Space-based observatories began to reveal brilliant X-ray sources buried behind the Milky Way's disk. Each one marked a deep gravitational hollow, a place where mass had gathered quietly over billions of years. Among these discoveries, one stood out with particular clarity. The Norma cluster, distant, immense, and heavy with dark matter, sat near the heart of this hidden region. Its hot gas traced a gravitational depth far beyond what visible stars could explain. Yet even Norma was not alone. It was part of something larger, woven into a network of mass extending far beyond a single cluster. Infrared light added another layer to this unfolding picture. Longer than visible wavelengths but shorter than radio, infrared light slips through dust while still carrying the glow of stars. Infrared surveys revealed thousands of galaxies previously erased from optical maps. Slowly, the zone of avoidance transformed from a blank stripe into a partially illuminated landscape, revealed piece by piece, wavelength by wavelength. No single method was enough. Radio waves favored gas-rich galaxies. X-rays highlighted massive clusters but missed the filaments between them. Infrared light traced stars but not the dark matter holding everything together. Understanding required patience, data combined carefully, biases acknowledged, limitations respected. Over time, astronomers began to assemble these fragments into three-dimensional models. They tracked not just where galaxies were, but how they moved. Galaxies became test particles, their motions responding to invisible contours in spacetime. Even where light failed, movement spoke clearly. Again and again, the calculations pointed toward the same dense region hidden behind the Milky Way. This shift, from brightness to motion, changed everything. It reshaped how scientists study not only the Great Attractor, but the hidden structure of the universe itself. Missions designed to map our own galaxy, like Gaia, refined our understanding of foreground dust, helping peel it away from distant signals. New radio arrays sharpened the picture further, revealing smaller structures nested within larger ones. Yet the Great Attractor never resolved into a single object with sharp edges. It resisted simple definitions. It was not a solitary giant, but a place where density rises, where filaments of the cosmic web converge and matter accumulates. A region, not a thing. This realization quietly overturned an earlier image. For years, the Great Attractor was imagined as a single colossal mass, pulling galaxies inward like a cosmic sinkhole. But evidence accumulated gently, steadily, until that image softened and dissolved. No single cluster, not even Norma, could account for the observed motions alone. The pull came from many structures acting together. The Norma cluster revealed itself as a major node, embedded within the broader Hydra-Centaurus region. This supercluster stretched across vast distances, its clusters linked by filaments rich in dark matter. Together, their combined mass created a wide gravitational basin, deep enough to shape the flow of galaxies across hundreds of millions of light-years. In this landscape, gravity is not a force reaching across emptiness. It is geometry. Mass and energy curve spacetime, and galaxies follow those curves as naturally as water flows downhill. Velocity reconstructions showed streamlines converging gently toward this region, slowing as they entered denser territory. Not falling, not plunging, drifting, guided. These conclusions rested on decades of careful distance measurements. By comparing how fast galaxies should recede with how fast they actually move, astronomers inferred where unseen mass must lie. Different methods, X-rays, velocities, lensing, arrived at the same answer. Consistency replaced speculation. The Great Attractor, it became clear, is a crowded crossroads in the cosmic web. Not unique. Not final. Simply nearby. When simulations of the universe evolved early density ripples forward in time, similar structures emerged naturally. Regions of enhanced density formed, drawing matter along filaments, creating coherent flows. The Great Attractor fit this pattern perfectly, remarkable not for its nature, but for its proximity. This understanding, galaxies are not racing toward a single point of no return. They move through overlapping gravitational influences, each shaping paths gently, collectively. Beyond the Great Attractor, even larger structures tug subtly, reminding us that no basin exists in isolation. To understand our own motion, you turn to the oldest light in existence, the cosmic microwave background. Its faint warmth carries a quiet message: our local group of galaxies is moving, steadily, through space. The pattern of that motion aligns with the direction of the Great Attractor, but alignment does not mean collision. When local motions are removed, our dance with Andromeda, the expansion of space itself, a broader flow remains. It extends across an immense region known as Laniakea, the supercluster that contains our home galaxy. Within it, the Great Attractor sits near the center of influence, shaping trajectories but not sealing fates. Simulations of the future show no dramatic plunge ahead. The Milky Way will continue drifting along curved paths shaped by many masses at once. Dark energy stretches space on the largest scales, preventing collapse into a single bound object. Gravity guides locally, expansion rules globally. Over unimaginable spans of time, the sky will change almost imperceptibly. Galaxies will shift. Patterns will evolve. Yet the stars of the Milky Way will continue their calm orbits, largely unaware of the galaxy's slow journey through the cosmic web. The story of the Great Attractor is not one of catastrophe, but of perspective. Our position inside the Milky Way once hid important truths. That same vantage point taught us humility, patience, and new ways of seeing. Tonight, as your thoughts slow, remember this: even when the universe seems obscured, its structure is still there, waiting to be traced by motion, by gravity, by quiet understanding. And as you drift toward rest, the hidden landscape beyond our galaxy continues its gentle work, shaping paths, guiding flows, and reminding us that even in darkness, the universe is deeply, calmly connected. As the measurements grew clearer, the words began to change. What once sounded like a fall softened into something gentler. Astronomers stopped speaking of descent and began to speak of flow. That shift mattered. Falling suggests a drop toward a single point. Flow describes motion guided by shape, a quiet response to a landscape of mass rather than a plunge toward an ending. In this calmer language, you are not tumbling through space. You are moving within it, following contours that were laid down long before the first stars formed. Seen this way, the local group becomes part of a slow migration through a structured universe. Not a journey with a destination, but a long participation in a pattern. Observation and theory meet comfortably here. Nothing in the data demands drama. The cosmic microwave background remains the steady reference beneath it all. This ancient light, released when the universe was young and nearly uniform, offers a frame untouched by nearby structures. Against it, astronomers can measure true motion, not just relative drift. With each refinement, the velocity of the local group becomes clearer, its uncertainties narrowing, its direction remaining consistent. Future surveys will not overturn this picture. They will simply bring it into finer focus. Missions like Euclid and the next generation of radio observatories are designed to trace dark matter with greater clarity, revealing how mass is distributed across Laniakea and beyond. These efforts will add detail, not contradiction. Confidence, not surprise. Whether we are falling toward the Great Attractor ultimately becomes a question of scale and of words. On small scales, galaxies do sink toward clusters. On vast scales, they trace paths shaped by many overlapping influences. Your galaxy belongs to the second story. It is guided by the Great Attractor, but not claimed by it. This reframing gently adjusts the future of the Milky Way. The events that will truly reshape it lie much closer. The slow approach of Andromeda, the distant merger still billions of years away. The motion toward the Great Attractor continues quietly in the background, a steady translation rather than a defining fate. Laniakea provides context, not a countdown. As maps extended farther outward, another subtle pattern emerged. The flow lines do not end at the Great Attractor. They continue beyond it, hinting at even larger concentrations shaping motion on still grander scales. The Great Attractor remains important, but no longer singular. It becomes one layer in a deeper gravitational terrain, stretching far beyond our immediate neighborhood. And then comes the most unsettling realization. Most of what does the pulling cannot. When astronomers tally every visible star, every cloud of gas, every dust-filled galaxy in the region, the numbers fall short. The observed motion demands more mass than light can provide. This is not a mystery born of imagination, but of repeated accounting that refuses to balance. Long before the Great Attractor entered the conversation, the same discrepancy appeared closer to home. Stars in spiral galaxies move too quickly to be held together by visible matter alone. Clusters show the same problem. Superclusters magnify it. By the late 20th century, this invisible contributor had a name: dark matter. Not because it hides intentionally, but because it neither emits nor absorbs light. In the realm of the Great Attractor, dark matter dominates. For every unit of mass in stars and gas, several more reside in this unseen form. In massive clusters, the imbalance can approach 5 to 1. Most of the gravity-shaping galaxy motion comes from matter that never glows. Galaxies, you learn, are not isolated islands. They sit inside vast halos of dark matter extending far beyond their visible edges. These halos overlap, merge, and stretch along filaments, creating continuous regions of enhanced mass. The Great Attractor lies where many of these structures intersect. Evidence for this invisible framework comes quietly but consistently. Gravitational lensing shows light bending where no corresponding light source exists. X-ray observations reveal gas heated by gravity deeper than stars alone could create. Radio and infrared surveys uncover hidden galaxies, increasing visible mass, but never enough to close the gap. Across every wavelength, the conclusion remains unchanged. On the largest scales, the universe resembles a web. Filaments, sheets, and nodes form a vast architecture, with dark matter as its scaffold. Ordinary matter drifts inward, lighting up only where the underlying structure already exists. The Great Attractor is one such junction, not an anomaly, but a natural feature of this design. Simulations reinforce this picture. Starting from the faint patterns imprinted in the cosmic microwave background, researchers let gravity shape the universe forward in time. Again and again, dense regions form. Matter flows toward them. The resulting patterns mirror what is observed around the Great Attractor today. When models ignore dark matter, the flows weaken. When it is included, the motions align with reality. This agreement has been tested repeatedly, across independent studies, across decades. Even dramatic events elsewhere confirm the same truth. In colliding clusters, visible gas can be stripped and slowed, while dark matter passes through almost untouched. Lensing maps reveal where the mass truly resides, often far from the brightest light. These moments make the invisible unmistakable. The Great Attractor does not need such spectacle to prove its nature. Its influence is quieter, broader, distributed across overlapping halos and filaments. The galaxies you can see trace only the peaks of a much deeper landscape. As you rest with this thought, the universe feels less threatening, more intricate. Motion replaces falling. Structure replaces mystery. And beneath all the visible beauty, an unseen framework holds everything together, patiently shaping the paths of galaxies, including your own, through a calm, connected cosmos. When you begin to ask how much of the cosmic pull comes from dark matter, another puzzle quietly resolves itself. The reason the Great Attractor was so difficult to recognize becomes clear. Traditional surveys were trained on light, not weight. Telescopes traced stars and glowing gas, but gravity follows mass wherever it hides. If most of that mass lives in dark halos, then maps built from light alone were always destined to underestimate what was truly there. The disagreement between motion and brightness was not a flaw in physics. It was the clue. That clue found support in the faint afterglow of the early universe. ESA's Planck mission studied the cosmic microwave background with exquisite precision, revealing tiny distortions imprinted by matter along the line of sight. These subtle patterns showed how mass bends space even when nothing shines. The The results fit seamlessly with a universe dominated by dark matter, including the regions where vast galaxy flows arise. This also explains why the Great Attractor never appeared as a sharp, compact object. Dark matter does not gather like stars into dense cores. It spreads outward, forming wide halos whose influence unfolds gradually across enormous distances. Gravity there works softly but persistently, guiding motion rather than causing sudden acceleration. What you observe in galaxy flows matches this expectation perfectly. The acceptance of dark matter was never rushed. Astronomers tested every alternative they could imagine. Modified gravity, hidden biases, flawed measurements, each was examined carefully and set aside only when the evidence refused to cooperate. The same discrepancy appeared again and again, across scales and methods, until the conclusion became unavoidable. Dark matter remained unseen at the particle level, yet its gravitational presence stood firm. For the Great Attractor, this means something quietly profound. Most of the pull-shaping galaxy motion comes from matter no telescope can photograph. The conclusion carries no drama. It simply reflects what the measurements demand. Seen through this lens, the region changes character. The Great Attractor is not a glowing beacon concealed by dust. It is a dense crossing of dark matter filaments, traced faintly by clusters like Norma and Hydra, Centaurus. The galaxies you see are markers, not the source. The true structure lies beneath the light. Future surveys will refine this picture further. Wide-area gravitational lensing studies and deeper redshift maps will sharpen our understanding of how dark matter is arranged within Laniakea and beyond. These efforts will not challenge the role of dark matter. They will define it more precisely, revealing its contours with increasing calm clarity. The answer to how much of the pull comes from dark matter is already written into the sky. Most of it does. Stars and gas are carried along, passengers within a far larger distribution that shapes motion silently, over immense spans of time. And when astronomers extended these mass maps outward, another realization emerged. The structures influencing the Great Attractor did not end there. They connected outward, linking to even larger assemblies farther away. When the maps reached beyond familiar territory, the story changed again. Galaxy flows did not slow. They did not settle. Instead, they continued onward, aligned towards something deeper, more distant, and more massive than the Great Attractor itself. This was not a single discovery, but a gradual recognition. As velocity maps expanded in scale and precision, the Great Attractor began to look less like a final destination and more like a waypoint. Galaxies seemed to pass through its influence, continuing along paths shaped by a broader gravitational landscape. What stood out in these extended views was the Shapley Supercluster, lying hundreds of millions of light-years away. It is one of the most massive concentrations of galaxies known nearby, a vast gathering of rich clusters, each wrapped in enormous dark matter halos. Together, they form a structure whose total mass rivals anything in our cosmic neighborhood. At first, its role was uncertain. Distance blurs precision, and astronomers are careful where uncertainty grows. But as measurements improved and flow maps deepened, continuity became hard to ignore. The same streams that converged near the Great Attractor continued onward, pointing unmistakably toward Shapley. This continuity forced a gentle revision of perspective. If the Great Attractor were the dominant endpoint, the flows should weaken beyond it. They did not. Instead, the motion remained aligned, suggesting that the Great Attractor sits along a slope leading toward an even deeper basin. Simulations of cosmic structure make this feel natural. When the universe is allowed to grow under gravity from its earliest fluctuations, smaller attractors form within larger ones. Local basins nest inside broader gravitational landscapes. In this view, the Great Attractor becomes a regional feature, embedded within the wider influence of Shapley. Galaxies do not plunge toward these regions. They drift along filaments, guided by overlapping gradients rather than pulled toward a single point. The influence of Shapley spreads softly across an immense volume, shaping motion without sharp borders. This understanding emerged slowly, strengthened by independent surveys and careful cross-checking. Infrared and radio observations reduced blind spots, making the continuity of motion increasingly difficult to dismiss. Shapley's sheer richness, its dense clusters and extraordinary mass, made it capable of influencing galaxy motion across staggering distances. The Great Attractor was not diminished by this discovery. It was placed into context. It became a foreground rise along a much larger gravitational slope, real and influential, yet not alone. This layered view of motion feels natural once seen. Galaxies orbit within groups. Groups drift within superclusters like Laniakea. And on still larger scales, immense structures such as Shapley shape the flow of entire regions of the universe. Each level builds upon the one below, without conflict, without urgency. Dark matter makes this coherence possible. Without it, such extended influence could not exist. With it, the universe gains depth and continuity. And as maps continue to stretch outward, subtle irregularities remain, hints that even these structures may not be the deepest ones influencing our motion. The river of galaxies may run farther still. What feels most unsettling is not that galaxies move, but that they move together. When the picture finally came into focus, you were no longer an isolated traveler. You were part of a vast, shared drift. Thousands of galaxies carried along gentle pathways, following the quiet shape of a universe built not around light, but around mass. This realization came into focus in the early years of the new millennium, when Brent Tully and his collaborators began reconstructing galaxy velocity fields using distance measurements of unprecedented precision. Instead of asking where galaxies were located, they asked how galaxies were moving. They separated the smooth expansion of the universe from the additional motions imposed by gravity itself. What emerged was not a scatter of random arrows, but a deeply organized flow. The approach was deliberate and conservative. Distances were estimated using multiple independent techniques, including the Tully-Fisher relation and surface brightness fluctuations. Redshift measurements supplied velocities, while careful corrections removed the effects of local interactions and the uniform expansion of space. What remained was the residual motion, the component driven purely by gravitational imbalance. When these residual motions were plotted in 3 dimensions, a striking pattern appeared. Galaxies traced long, continuous paths. These paths converged toward regions of higher mass density and curved away from vast cosmic voids. The motions resembled currents shaped by an uneven gravitational landscape. This was not a poetic analogy. It was a direct visualization of how matter responds to gravity on the largest scales we can measure. From these reconstructions, the concept of Laniakea took shape. Laniakea is not a cluster, not a traditional supercluster, and not a gravitationally bound object. It is a basin of attraction, a region of space defined by motion rather than appearance. Within its boundaries, galaxy motions converge toward a shared gravitational low point. Beyond those boundaries, the flows turn elsewhere. The Milky Way lies well inside this basin. So do Andromeda, the Virgo cluster, and thousands of other galaxies spread across roughly 160 megaparsecs. This scale was not chosen arbitrarily. It emerged naturally from the velocity field itself, where flow lines diverged and the basin's edge could be traced. Laniakea was mapped by motion, not by light. What made this result compelling was its independence from any single dataset. Different surveys, using different telescopes and distance indicators, produced compatible flow patterns. The precise boundary of Laniakea shifted slightly as measurements improved, but the overall structure remained stable. That consistency gave astronomers confidence that they were observing a real feature of the universe. The idea of a basin of attraction follows directly from gravitational physics. Where mass density is higher, spacetime curves more strongly. Galaxies respond by gently adjusting their trajectories toward regions of deeper curvature. Over immense distances, these small accelerations accumulate into coherent motion. Laniakea represents one such region, where accumulated mass dominates the surrounding gravitational field. Near the center of this basin lies the Great Attractor. It is not the only mass concentration within Laniakea, but it marks a significant low point in the gravitational landscape. Velocity maps show galaxies flowing toward it from many directions, including our own local group. This clarified the role of the Great Attractor as a central feature within a larger structure, rather than an isolated mystery. The mapping of Laniakea reflected a broader shift in how astronomers think about cosmic structure. Earlier models defined superclusters by counting galaxies or measuring luminosity. The Laniakea map defined structure by motion. It asked a different question, not where galaxies are, but where they are going. That change in perspective revealed connections that brightness alone could never show. Data from NASA and ESA played a quiet but essential role. Observations of the cosmic microwave background provided an absolute reference frame, ensuring velocities were measured consistently across the sky. Infrared and radio surveys filled in regions obscured by dust, especially near the zone of avoidance. Each contribution reduced uncertainty and sharpened the flow map. What emerged was a calm revelation. Galaxy motion on the largest scales is not chaotic. It is highly organized. Galaxies follow paths defined by the distribution of dark matter, which forms the invisible framework of the cosmic web. Laniakea is one basin within that web, carved by the accumulated mass of clusters, groups, and filaments. Importantly, Laniakea is not gravitationally bound in the way a galaxy cluster is. Dark energy and cosmic expansion prevent the entire region from collapsing into a single object. Galaxies within Laniakea are guided by its gravitational gradient, but they are not destined to merge at its center. The basin defines motion, not fate. This distinction resolved much of the confusion surrounding early descriptions of the Great Attractor. Rather than imagining galaxies falling into a hidden monster, astronomers could now describe a smoother, distributed process. Galaxies move along gradients shaped by many overlapping mass concentrations. The Great Attractor is a prominent feature within that flow, not its final destination. The velocity field also revealed neighboring basins. Just beyond Laniakea's boundary, flow lines bend toward other mass concentrations, including the Shapley Supercluster. This confirmed that Laniakea is one region within a larger hierarchy, influential, but not universal. One of the most powerful aspects of the Laniakea map was what it did not assume. It relied neither on models of galaxy formation nor on expectations about how mass should be distributed. It relied on motion alone. If galaxies moved in a certain way, then the mass responsible for that motion had to exist, whether visible or not. This made the result remarkably robust. The emotional impact of the discovery was quiet, but lasting. For the first time, astronomers could place the Milky Way within a clearly defined large-scale flow. Our galaxy gained an address within a dynamic structure shaped by gravity. The map provided context rather than drama. As Carl Sagan once emphasized, understanding comes from placing ourselves within a larger framework. Maps change our perspective not by diminishing us, but by locating us accurately. The Laniakea map did exactly that, using motion as its guide. As datasets continue to grow, the boundaries of Laniakea will be refined. New distance measurements and deeper velocity reconstructions will adjust details, but the core result is unlikely to change. Galaxies move in organized flows, and the Milky Way is part of one such river within Laniakea. The flow is real because gravity demands it. And yet, the map also pointed outward. At its edges, motions behave less predictably. Some flows appear too large to be explained by known structures alone. These subtle anomalies hint at influences extending beyond the boundaries we can currently chart. That unresolved tension carries us forward. Could there be even larger attractors beyond the edge of what we can observe? The most unsettling possibility raised by modern cosmology is not that we are being pulled by something unseen, but that the pull may not stop where our maps end. When astronomers extend measurements of galaxy motion to the largest scales accessible to observation, some patterns remain that cannot be fully explained by the Great Attractor, Laniakea, or even the Shapley Supercluster. These appear as large-scale bulk flows, gentle but persistent motions stretching across hundreds of millions of light-years. The cosmic horizon is not a wall, but a limit set by time and the finite speed of light. Beyond it, light has not yet reached us. Gravity, however, is not stopped by visibility. If mass exists beyond our observable horizon, its influence may still be felt. Early discussions of these bulk flows were cautious. Distance uncertainties grow with scale, and systematic errors can imitate coherent motion. Astronomers refined methods, combined independent surveys, and tested every bias they could identify. Some early claims softened as data improved. Yet even with conservative analysis, certain anisotropies remained. Clues also came from the cosmic microwave background. Its large-scale patterns encode information about density variations in the early universe. Missions such as COBE, WMAP, and Planck showed that while the standard cosmological model explains most features beautifully, a few large-scale anomalies remain subjects of careful study. These observations raise a question grounded not in speculation, but in physics. If mass distributions exist beyond our observable horizon, could their combined gravitational influence subtly shape motion within it? General relativity allows for this. Gravity responds to mass, energy whether or not it can be seen. Inflationary cosmology provides context. It predicts that the universe beyond our observable region may be far larger and more structured than what we can detect. As Alan Guth once noted, there may be an enormous amount of universe beyond the part we can observe. This does not imply hidden monsters waiting in the dark. It reflects scale. In such a universe, structures beyond the horizon are not exotic. They are expected. And while they cannot be observed directly, their gravitational influence may still leave faint signatures in the motion of galaxies we can see. Especially over long timescales, astronomers have explored the possibility that large-scale motions may be influenced by structures extending far beyond what we can directly observe. One way they approach this question is through simulation. By modeling universes with slightly different large-scale density distributions, researchers examine how bulk flows respond. In some scenarios, long wavelength density gradients naturally produce coherent motions similar to those observed in real data. These models require no new physics, only subtle variations in initial conditions set early in cosmic history. Observationally, the challenge lies in separating local influences from truly horizon-scale effects. Known structures, such as the Shapley Supercluster, exert strong gravitational pull and must be accounted for with great precision. When these contributions are carefully modeled and subtracted, any remaining motion becomes the signal of interest. This process is delicate and often debated. Data from galaxy surveys, including those supported by NASA and ESA, show that most observed flows can be explained by known large-scale structure within the observable universe. Yet the margins are not zero. Some analyses report small residual motions that invite continued scrutiny. These are not taken as definitive evidence, but neither are they dismissed outright. The study of anisotropy offers another perspective. On the largest scales, the universe appears remarkably uniform, yet small directional differences persist. These differences are measured in galaxy distributions, velocity fields, and the cosmic microwave background. Most align well with expectations from cosmic variance, but a few correlations remain unexplained. Importantly, astronomers resist framing such anomalies as proof of hidden attractors. The history of cosmology is filled with discrepancies that dissolved as data improved. Better calibration, deeper surveys, and refined statistical tools often resolve tensions without invoking unseen structures. This caution is not skepticism, but discipline. At the same time, the possibility itself reshapes perspective. The Great Attractor and the Shapley Supercluster taught astronomers that unseen mass can dominate motion on scales once thought fully understood. It is therefore reasonable to ask whether even larger scales might hold additional surprises. The question is not whether they exist, but whether their influence can be measured. Future missions will help clarify this. The Euclid mission and upcoming radio surveys aim to map galaxy distributions and weak gravitational lensing across unprecedented volumes. These observations will sharpen constraints on bulk flows and test whether residual motions persist as data quality improves. The James Webb Space Telescope, though focused on deep field observations, contributes indirectly by refining models of structure formation. If residual flows remain after these efforts, the implications would be profound but not destabilizing. They would suggest that our observable universe responds to conditions set on even larger scales, a result that would align naturally with inflationary predictions. If the anomalies fade, the lesson will be equally valuable, confirming that known structures fully account for observed motion. In either case, understanding advances through restraint and evidence. The idea of unseen attractors beyond the cosmic horizon is neither speculative fantasy nor established fact. It is a question that emerges from precise measurement and remains open because the universe is vast and our observations are finite. Carl Sagan often emphasized that science is a way of asking questions that can be answered, or at least constrained, by evidence. He noted that the observable universe is not the same as the entire universe, a distinction grounded in physics rather than imagination. That distinction frames this discussion. The Great Attractor began as an anomaly in galaxy motion and became a well-defined structure once enough data were gathered. The Shapley Supercluster extended that picture further. Now the edge of observation marks another boundary, where motion meets uncertainty. What remains clear is that galaxy motion is one of the most sensitive probes of mass distribution. Light tells us where stars are. Motion tells us where gravity comes from. When the two disagree, astronomy listens carefully. As velocity maps reach their limits, interpretation becomes cautious and methodical. Astronomers do not rush to fill gaps with speculation. They wait for better data, refine models, and test alternatives. This patience transformed the Great Attractor from rumor into structure. The possibility of even larger hidden influences therefore stands not as a claim, but as a boundary marker, showing where current knowledge ends and future observation must begin. Stepping back, the broader picture comes into view. The Milky Way's motion, traced through redshift surveys, cosmic microwave background measurements, and velocity field reconstructions, shows that our galaxy is embedded within a structured network of mass extending across immense distances. This understanding emerged not from a single experiment, but from the convergence of many independent observations. The cosmic microwave background provides a universal reference frame. Galaxy surveys reveal deviations from uniform expansion. Weak gravitational lensing maps mass whether it shines or not. Together, they show that motion traces the geometry of mass in the universe. The Great Attractor plays a central role in this story, not because it is unique, but because it is close enough to study in detail. It demonstrated clearly that visible matter alone does not define structure. The gravitational pull guiding our motion arises from the combined mass of clusters, filaments, and dark matter halos woven into the cosmic web. In this web, matter is not evenly distributed. Dense nodes form where clusters gather. Filaments stretch across tens and hundreds of megaparsecs. Vast voids open between them. Galaxies move along this network, responding to gradients in mass rather than orbiting a single center. The Great Attractor marks one significant node within this system. Seen this way, the universe is not a static backdrop, but a dynamic landscape shaped by gravity over billions of years. Where mass concentrates, trajectories bend. Where mass thins, motion accelerates away. These coherent flows can be mapped, tested, and compared with theory. When simulations evolve the tiny density variations seen in the cosmic microwave background forward in time, the resulting structures closely resemble what we observe today. Dark matter plays a crucial role in this picture. Without it, the observed flows would be far weaker and less organized. Visible galaxies alone cannot account for the depth and reach of gravitational basins like Laniakea. Dark matter forms the unseen framework within which luminous matter resides, resolving earlier confusion about whether galaxies were falling into isolated objects. They are not. They are moving through a continuous gravitational landscape shaped by overlapping influences. The language of basins and flows reflects measured behavior, not metaphor. It describes how gravity operates across scales where no single object dominates. The Laniakea map made this clear by defining structure through motion rather than brightness, revealing the dynamic shape of the universe instead of a static snapshot. From this perspective, the Milky Way's motion is not unusual. It is typical. Our solar system, our star, and our planet are carried gently within a larger flow, smooth and gradual, unfolding over hundreds of millions of years. The universe displays large-scale organization not because it is directed, but because gravity shapes an initially uneven distribution of matter over cosmic time. The Great Attractor also reminds us of observational humility. For years it lay hidden behind the Milky Way's dust. Its influence was detected before its structure was seen. Motion revealed what light concealed. This lesson echoes throughout cosmology, where indirect evidence often leads discovery. As surveys expand and measurements improve, details will sharpen, but the core conclusion is unlikely to change. The universe is structured. Motion is organized. Gravity connects regions across vast distances. Being pulled by the Great Attractor tells us that our galaxy's path is not random. It is shaped by a network of mass spanning hundreds of millions of light-years. The universe reveals its shape through motion. If you are listening as the night settles in, let that steady cosmic flow carry your thoughts toward rest. The galaxies continue their slow, patient journey. And for now, so can you. Good night.